Tuning of flow control loop using DeltaV DCS and MATLAB. Abstract process management instrumentality is meant to information from input modules, process the information, work the plants on a gentle state basis and square measure, and decide control actions to be signaled by the output. Most significant to work out the performance of automatic modules. The field inputs and outputs can be analog signals. System management of the method needs thorough, e.g. 420 mA DC current loop or two-state signals that management data, the behavior of the method parts, method switch either on or off, such as relay contacts or a details, and interrelation at intervals the sections of the semiconductor switch. DCS has separate cards for do method plant. Flow management encompasses a big selection of application in method industries. In 90% of method AI, AO, and each card having 8 channels. Management applications have a tendency to manipulate the flow to get desired output. The aim work centered on pelvic 2. Literature survey. Inflammatory disease standardization methodology and flow. Madhuri Jarang implemented PID tuning of level control. Management loop implementation. Flow is dynamic loop using DeltaV DCS and concluded PID tuning using parameter, thus totally different standardization strategies for IMC gives best response for FOP process model. Standardization pelvic inflammatory disease Viz and Ziegler Nichols standardization methodology square measure. Sujit Anandrao Gajdhane in his paper Modeling Thought about dominant flow victimization DCS is that the simulation and control of flow tank system described. Best combination. DCS provides advanced management ways to regulate the method parameters. Thus we have a tendency various approaches on how to determine process transfer to square measure attending to interface flow management function involving flow control loop using ZN method, loop with DCS. Study its behavior for a step input relay auto tuner etc. to modification verify its transfer operate of our model victimization advanced DCS management functions. They. J.S. Rajashankar in his paper Flow Control Loop Analysis. Comparative studies show that the simulation's results vary. For system modeling and identification studied and analyzed. From real-time implementation results. Flow control loop components, whereby experimentation carried out on an industrial-type control valve, I/P. Keywords PID tuning, Ziegler Nichols, internal model. Converter, orifice in the laboratory. Effective data. Control, MATLAB, DeltaV DCS. Collection of these components, consisting of literature. Introduction gathering and some tests such as step and vibration on these distributed control system, is a computerized control components, is performed using which modeling equations system for a process or plant usually with many control are formed in MATLAB. 3 loop, in which autonomous controllers are distributed throughout the system, but there is no central operator. Jack in his paper an extended model of a level and supervisory control. This is in contrast to systems that use flow control system providing an improved transfer centralized controllers. Discrete controllers located at function model of this system's level and flow control central control room or within a central computer. The DCS loops results are obtained using MATLAB system concept increases the reliability and reduces the installation identification toolbox after data acquisition in LabVIEW cost by localizing the control functions near the process for plant, with remote monitoring and supervision. Today the 3. Process setup. DCS and SCADA systems are very similar, but DCS tends the process hardware setup is shown in the given Fig 1 to be used on a large-scale process plant where high the flow control loop components are as, air filter, regulator, pneumatic control valve, vortex flow meter, flow transmitter. The pressure required for control valve is 3 to 15 Sig. In this system, capacitance type flow transmitter is used to measure the flow of tank 24V. Power supply is required for flow transmitter. It is a 4-wire transmitter. An output of transmitter is 4-20 mA. Fig. 1. Process setup. 3. System description as shown in Figure 2 below. Flow control loop system is basically a feedback control system. The flow from the pneumatic control valve is given to the turbine flow transmitter, which converts the input flow into 4-20 mA signal. This 4-20 mA signal is then given to the DCS system with the help of twisted pair cable that carries 4-20 mA signal. The DCS involves a PID controller functional block which takes care of making the controlled variable closer to the set point value. It does so by calculating the values for proportional gain, reset, and rate parameters by setting the mode of the controller in the auto state. The values for proportional gain, rate, and reset are calculated using Ziegler Nichols tuning method. In this way, DCS will make sure that the controlled variable, which in this case is flow, reaches closer to the set point value. Other tuning methods like internal model control were also considered. The output of DCS goes as an input to the current to pressure converter, which held responsible to close or open the control valve depending upon the output of the DeltaV DCS. In this way, the flow inside the loop will said to be controlled as per the requirement or set point value. The block diagram of the proposed system is as follows. For system identification. This is one of the powerful but complex controller mode combining proportional, integral, and derivative control modes. It has following advantages. A. 1-to-1 correspondence between P and EP. B. Eliminates offset of P mode. C. Provides fast response. Mathematically, PID controller is written as T. P equals Kp.EP plus Kp.Key. EP plus KPKD, DEP/DT, plus pi, 0, 0 where, Kp equals proportional gain, key equals integral gain, Kd equals derivative gain. Kp is expressed in terms of proportional band Pb, key is expressed in terms of integral time Ti, and Kd is expressed in terms of derivative time Td. For better control, Pb should be less, Ti should be less, and Td should be high. PID controller can be used as P controller by removing I and D actions. Integral action can be removed by using Ti equals maximum. Derivative action can be removed by using Td equals 0. Similarly, PID controller can be used as Pi and PD controller, by removing D action, Td equals 0, and I action, Ti equals maximum, respectively. Fig. 3. Step response of the system. This graph is recorded in process history view in DeltaV of real-time experimentation in open loop. To find the transfer function of open loop system, above graph is used. Calculate the transfer function by 63.3% approach of process variable. Following is the transfer function of the system. After finding out the transfer function, the values of Kp, Tp are obtained, and finding out the PID tuning parameters in MATLAB, using following method. Internal model control, IMC. The IMC method, like the DS method, is based on an assumed process model and leads to analytical expressions for the controller setting. These two design methods are closely related and produce identical controllers if the design parameters are specified in a consistent manner. Analog input block. Analog input block uses only single analog measurement value and status from an I/O channel. Transmitter's 420 mA signal cab be taken as input value. Generally, we use CH2 of analog input card for the flow transmitter. Analog output block. Analog output block is used to give an analog output value to a field device with the help of a specified I/O channel or field bus device. Generally, CH3 of analog output card is used to provide the output of control valve. PID block. PID block gathers all the necessary logic required to perform proportional integral derivative, PID, control, analog input channel processing and analog output channel processing in a single function. The following figure shows the PID tuning parameters of IMC in PID parameters block. V results in analysis. 1. Step response for IMC using the values calculated theoretically showed better result as shown in the table and helps to meet the required specifications. The output response for IMC in AutoTuner in MATLAB is shown in the figure 5.1 below. The following table shows the values obtained from the responses. 2. Step response for PID AutoTuner, MATLAB tool, showed slow response comparatively with much higher rise time and settling time. The values are mentioned in the table. The step response using PID AutoTuner is as shown in the figure 5.2 below. Table number 1 keeping the Kp value constant and Kd value 0 and using trial and error method for PID and IMC technique. 6. Conclusion. The 3 tuning methods, internal model controller, PID tuner, MATLAB tool, and the trial and error method are studied with their implementation for flow control loop. The gain values are determined by the trial and error method. As per the simulation results, it seems that the trial and error method showed good response to a step change, but the settling time observed was more. The PID tuning, using AutoTuner in MATLAB shows high rise and settling time compared to the IMC technique. By using trial and error method for PID tuning, the flow control loop performs better. In addition, IMC technique should also be considered to improve the system response.